supersymmetry colliders based on a couple of works that I have worked on in the last 1 year. As Shinja already noticed, people may wonder if I made a typo in the title and wonder if we should be supersymmetry of future collider. But I intentionally made this title because many of you have already heard about future collider aspects a couple of times, but not many of you have heard about future supersymmetry aspect. And future supersymmetry that we will confront in the future has several qualitative differences compared to previous SUSY that we have been studying. So I wanted to emphasize those aspects a little bit, so I made up this title. So my talk is about these three aspects. First, future collider prospects. The second, future SUSY differences compared to previous SUSY. And also, I would like to present a few possible future searches that could be standard in the near future. So future collider prospect, I will present standard search prospect at 100 TeV collider and various other collision energies. But interesting question would be, is it good enough? And how well do we need to do? But answering these questions are model dependent. So I will address these questions in the future SUSY framework, focusing on the Wino thermal dark matter or Higgsinos thermal dark matter. And also one may wonder, is the future collider study simply a scaled up version of the 8 TeV or 14 TeV study? The answer would be yes or no, and I will also address the question in the future SUSY framework. So what's future SUSY? So by this future SUSY, I generally mean a SUSY that we will confront in the future. So overall, superparticle mass scales are heavier, but in particular, I will focus on the cases where fermionic superparticles such as gauginos and Higgsinos are lighter, and their masses are about a few hundred GeV up to a few thousand GeV, and all the scalar superparticles are heavier. So future SUSY doesn't have to be in this kind of special spectrum, but there are good reasons to study this kind of spectrum that I will discuss in a moment. If you have an overall heavier superparticle, in general, gauginos and Higgsinos are likely well separated in mass. So the heaviness and the well separatedness is defined with respect to the electroweak scale. So if gauginos and Higgsinos are much heavier than electroweak scale, generally, they are likely well separated in mass compared to the electroweak scale. So mass separation is much larger than electroweak scale. Then they are likely a pure state. Mixing is minimized because mixing is induced by electroweak back scale release. And these two statements have interesting implications in the future collider studies that we have to utilize. So along the discussion of discovery potential, I will address these features. So the statement of pure gauginos and Higgsinos imply that Higgsinos are more like a Dirac and gauginos are Majorana. So we can prove the Dirac nature of the Higgsinos and Majorana nature of the gauginos generically in the future SUSY. And there is a something so-called the gaugino code that I will introduce in a moment. And this becomes a primarily important observable in the near future that can be observable. And being they are well separated in mass means that decays between the heavier states to the lighter states are boosted. So their decays are related by Goldstone Equivalence Theorem inherently. So there are new simplifying relations show up, and they can modify the strategies in the future collider searches. Also, if you have a multiple particles well separated in mass, you have a several disparate mass scales. So in quantum field theory, higher order correction, you inevitably have large logarithms induced in the lower spectrum of your theory. And resummation of those large logarithmic factors are needed in order to have a reliable prediction. So these three aspects will be discussed along the discussion of future potential. So before I go on, let me briefly introduce this gaugino code. So this is basically means that gaugino mass ratio becomes a primary observable and also critical variable determining the future discovery potential. And gauginos are leastly model-dependent field encoding SUSY breaking mediation information. So these people have categorized the gaugino mass in the majority of SUSY breaking models. So in the first model, there is an M-Sugura pattern of the gaugino mass. Gaugino mass is proportional to gauge coupling itself. So the free gaugino mass ratio is given by 1 to 2 to 6, given by alpha 1, alpha 2, alpha 3. And the second category, so-called AMSB anomaly mediated pattern, the gaugino mass is proportional to beta function times gauge coupling. So the ratio is changed to be 3 to 1 to 8. And lastly, in the Mirage pattern, gaugino mass is a linear combination of these two. But in all these models, gaugino masses are functions of gauge coupling or beta function, which is well measurable and well calculable. So gaugino mass ratios are predictable. And if you measure 1 or 2 particles and measure these gaugino mass ratios, you can sort of deduce the SUSY breaking mediation information. So this becomes an important parameter in the future.
I don't quite remember. Is there also a pattern for the general gauge mediation?
Yeah, you can then generalize this.
Oh, okay.
Relation.
But that's
this
not,
is
not
for
so
special
simple.
models.
Okay.
Oh. And also the future SUSY spectrum that I will focus on, where the fermionic particles are lighter and scalar superparticles are heavier, is somewhat well motivated. First of all, it's consistent with all data. Null LHC flavor CP results and heavy Higgs boson masses are consistent with this model, or can be an even prediction of this model. And with some exaggeration, I would say a half of universe is generically giving this kind of split supersymmetry spectrum, because fermion mass can be easily protected by any global symmetry under which your SUSY breaking fields are charged under. The scalar masses are more or less a free parameter. So whether your SUSY breaking field is charged under some global symmetry or not, you can have split spectrum or not in general. So in that sense, I say a half of universe is generically this split SUSY line. So it's very generic and possible. And also there are many attractive phenomenologies such as gauge coupling unification and dark matter candidates in this model. But although we are considering overly heavy spectrum, particles cannot be arbitrarily heavy, constrained from dark matter relative density and the Higgs boson mass. If you have a too heavy LSP particle, your dark matter relative density will be too high to be consistent, and also Higgs mass to be too high to be consistent. So there are two important mass scales. If Higgsino is dark matter, 1 TeV Higgsino can give you the right amount of relative density. If Guino is dark matter, roughly 3 TeV can give you the right relative density. And generally, heavier Higgsino dark matter or Wino dark matter give you too much relative density, so it's constrained. But it's not a mathematical theorem. There's always a loophole, and you can modify the cosmological history to make theory possible. But these are important mass scale we need to test, and we can target in the near future. So we need some specific number for the near future. That's very useful. And third aspect, I will present a few new searches that is not yet standard, but should be standard because it's very useful and powerful. There are two searches I'm talking about. One is new limits on line stops from stoponium. Stoponium is a bound state of stop and anti-stop. But the stoponium search can fill all inevitable gaps in the current collider searches, and their model dependencies are different from usual collider searches. So I will briefly talk about it in the last part of my talk. And also displaced decays can show up quite often from gravitino or Higgsino LSP, or when you have a small RPD coupling, these displaced decays can often quite often. So now I'll start with the standard searches. First, gluino pair, and second, NLSB electroweakino pairs. And there are also many other results on stop pair production, monojet plus missing energy, and various others, but I will talk about these two today. So first in the gluino pair searches, so I will focus on Wino thermal dark matter scenario, and gaugino code can be useful here, and resummation is essential in these searches. So here's a exclusion prospect at various energy of PP collider and 5 sigma discovery prospect. And gluino pairs are produced, and each gluino decays to QQ bar and LSP. So you have 4 quarks and missing energy in the final state. Traditional M effective is good enough. M effective means a scalar sum of PP or missing energy of everything you observe in the final state. So it works, and no fancy technique is needed. And at 100 TeV collider, roughly about 11 TeV gluinos are discoverable, and up to about 14 TeV gluinos are excludable. But the question is, are these numbers are good enough, and what does it mean to your favorite models? Before I go on, one interesting feature of the discovery prospect is this. When the gluino and your LSP are well separated in mass, below this black line, the discovery prospect only depends on the gluino mass in some sense. Okay. Your LSP mass, it is essentially massless particle, and it doesn't matter in the collider prospect. It has a very interesting implications, because if your model has such a well separated mass, you can plot everything in terms of gluino mass versus collision energy. LSP mass doesn't matter here. So here I'm considering AMSB model, where Wino can be a dark matter. And if you assume AMSB model, there is a certain relation between gluino mass and the Wino mass. The ratio is about A. And this ratio is largest among all 3 gaugino code models that I have discussed. So for the given LSP mass, this AMSB model might be the model which is most difficult for the discovery, because gluino is the heaviest. Anyway, so here I show you gluino mass and corresponding Wino mass here, and PP collision energy, and contours are luminosity needed for the 5 sigma discovery of the gluino pair. Okay. So previously I said 3 TeV Wino can give you the right thermal relic density, and testing this model up to this scale is very important. But to do so, 100 TeV collider, which is discussed widely nowadays, is not enough still. But interestingly, 200 TeV may be able to do so with order 100,000 inverse femtogram of data. So it might be good to keep in mind this 200 TeV collider. If financially and technologically similarly challenging, we may consider 200 TeV. Of course, the higher the better. And now I'm going to show you the same discovery prospects in another plane. So now I have a LSP mass here, and ratio of the gluino mass over LSP mass. And contours are luminosity needed for the 5 sigma discovery. And I also showed the gaugino mass ratio for certain models, AMSB model and MSUGRA models. So if your favorite model predicts a certain ratio between gluino and the LSP, you can look at this plot and just read the discovery potential. If gaugino mass ratio is such a useful observable and important parameter, then this plot might be very, very useful.
Is there an estimation of the how much luminosity we can get, like per year, like some kind of rough time scale?
I don't know, but the more running, you can get more data.
Yeah, that I know, but I'm just wondering, like, if, for example, 20,000 with SPI, like crazy, or you know.
Right. People talk about 1,000 or 3,000 inverse femtogram in 10-year time period.
Okay.
So maybe reachable in the far future. Yes, that's why I said that here.
Yeah,
Here
okay,
you
so
need
the
huge
proper
amount of
know-how.
luminosity, but here order 1,000 data, which might be possible.
Why is it that, is there some basic reason why luminosity should be going up as you go to higher?
Luminosity is going up.
Well, yeah, because you're talking about, nobody's talking about 100,000 femtobarn, inverse femtobarns at the 14 TeV and LHC. So I'm wondering, is there something that makes it easier to achieve, or is it just that the technologies, everything is going to get better somehow, or is there some physics reason why? I would think you build the ring as small as you can, so you're still worrying about losing energy and so on, and losing things.
100 TeV collider would have a lot higher luminosity than the LHC.
Why?
So as proton beams get to higher energy, they get smaller. You win big with both beams by the square, and so.
So that's just a question of whether you can maintain focusing over the big.
You build the experiment.
Can you build it? So I see. Okay, so there is a good. Okay.
Yeah, no, it's real.
Okay. Okay.
Okay. But for Higgsino dark matter, there can be no definitive coverage because a priori there is no relation between Higgsino mass and gaugino mass. So the ratio can be anywhere if your Higgsino is the dark matter. Anyway, this is a useful presentation for the future SUSY search if the gaugino code is such an important parameter. Oh, and if your quarks are much heavier than the fermion superparticles, as I said, there is an inevitable large logarithms induced in the gaugino mass spectrum. So these colored bands are those higher order uncertainty induced by heavier quarks. And if your quarks are 1 factor heavier than the fermion mass, your gaugino mass ratio is raised up to about 9 instead of 7 or 8. And there's also tangent beta and Higgsino mass dependencies. So these ranges are spanned by those underlying parameters in addition to higher order scale uncertainties. So by adding higher order correction, in general, scale uncertainty is reduced, but also underlying parameter dependencies is enhanced. So overall, let me come back here. So overall, still 20 to 30% uncertainty remains, even after including higher order correction. So more dedicated effective theory calculation of the higher order correction may be needed. So in our calculation, we didn't build a dedicated effective theory by integrating out heavier quarks or heavier particles, but we just add these 3 corrections to the leading order prediction. So first correction was NLO matching correction, where the SUSY breaking mediation is transmitted to the visible sector. So when you integrate out messenger sectors, you get a visible superparticle spectrum. But you can have NLO corrections in the matching correction. But fortunately, those matching corrections are mostly model independent at the NLO level due to gaugino screening theorem, or anomaly is 1 loop exact. And then we do the 2-loop RG evolution from the matching scale down to the TD scale where we observe the particle. And this 2-loop RGE resums next to leading logarithm, which is formally the same order as 1-loop finite corrections. And then at the low energy, we add the 1-loop threshold correction, which basically transform your Lagrangian running parameters into observable parameters. For example, gaugino pole mass, which is observable, is written in terms of your Lagrangian running masses. So at the leading order, they are equal, but at the higher order, they are not equal. So in order to write pole mass in terms of Lagrangian parameter, you need to add these threshold corrections. But if you had effective theory construction, this 1-loop threshold correction can show up as an RG evolution or operator mixing, so you can track the origin of the 1-loop threshold corrections. But we didn't do it here. So more dedicated calculation can improve the accuracy and tell you more about it. So that's all for the gluino pair. Now I'm going to talk about NLSP electroweakino pair prediction. Here I will focus on Higgsino thermal dark matter and U relations of the Higgsinos decays from Goldstone Equivalence Theorem. So electroweak gaugino pairs are produced chargino-neutralino or neutralino-neutralino, chargino-chargino. And if you have all the scalars much heavier than fermions, they always decay via gauge bosons or Higgs boson, as shown here. And they can eventually decay to quarks and leptons, but multi-lepton plus missing energy are representative signatures of this case. So I will focus on various multi-lepton plus missing energy searches. And decay modes are inherently related by Goldstone Equivalence Theorem. So here's the first simple example. Wino is the NLSP, and Bino is the LSP. So Wino pair is produced, and they decay to Bino, giving various multi-leptons. So here's a discovery reach at 100 TeV, and exclusion reach at 100 TeV. I chose specific parameters. The thing I wanted to mention here, discovery reach is also important and interesting. But I chose specific parameter, but if I vary this parameter, we get very different results. All this matter, Wino is NLSP and Bino is LSP, same mass spectrum, but just different tangent beta and different sign of gaugino and the Higgsino masses. Then you have a very, very different discovery prospect. Because branching ratio into Higgs and Z boson depends on those parameters significantly.
There's this, the bound is getting, on some of these plots, like the lower left plot.
Here?
Lower,
Here?
yeah, that one.
Okay.
So for the bound actually gets, the search gets less sensitive for small LSP mass.
Yeah.
So what's going on there?
So that's also because of the branching ratio into Z boson. It's maximum here,
Oh,
and
okay.
it's smaller here.
Okay.
It's all about branching ratio into Z versus
Okay.
Higgs boson. So this is a slide from Atlas speaker Frank Werthwein in the US Atlas physics meeting, and he was wondering, so currently all the searches are presented in terms of simplified models where you assume 100% branching ratio into the interesting decay modes. But if we are too much influenced by simplified models, because we have various different branching ratio depending on parameters. But if your model predicts a certain range of branching ratio or certain types of branching ratio, then you may have to focus on them. But as we saw, any kinds of branching ratio is possible in this case. So maybe simplified model is the best approach, and you can just interpolate between various different simplified models to get the correct results for your favorite model. The situation is different when your model has Higgsinos as an LSP or NLSP. If Higgsinos are LSP or NLSP, those parameter dependence essentially vanish. And always NLSP decay into LSP to Z or Higgs equal each other. So this one plot is enough for all those parameter choices. And maybe this model may serve as an alternative, true simplified model with this relation, branching ratio to Z and Higgs equal. Why Higgsinos are special? So Higgsinos have two nearly degenerate and indistinguishable neutralinos. And one of the Higgsino decays more promptly to Z boson, and the other Higgsino decays more promptly to Higgs boson. But what we observe at the collider is not individual decays because they are almost degenerated, indistinguishable. So we have to add all those effects. And by adding two Higgsino decays, we end up getting this relation. Individual Higgsino decay doesn't satisfy this relation, but adding all this, we have this relation, and that's an observable relation. And it's a more or less a Dirac nature of the Higgsino. Majorana nature, we know doesn't satisfy this nature. And this is generically true in the future SUSY framework, because Higgsino is generically Dirac and pure states. And this relation was easiest to derive using the Goldstone Equivalence Theorem. So these are most general partial width Z boson versus Higgs boson written in terms of respective couplings, gaugino, Higgsino, and gauge boson and Higgs boson. And those coupling doesn't seem to have any relation at face value. But in the future SUSY framework, if you use the Goldstone Equivalence Theorem, the Z boson partial width can be written in terms of Goldstone partial width. And this Goldstone coupling and Higgs boson coupling have almost identical primary dependence, except for this sign. So it's much more analytically tractable. And based on this equation, and using this relation, you can get this relation. So indeed, using the Goldstone Equivalence Theorem, proving the Higgsino relation was much easier. And this relation is generally true even with the many non-MSSM neutralinos. Higgsino or gravitino, all these relations are satisfied. Just different tangent beta dependence. The signs are almost opposite. And when you add two Higgsino effects, you get the same branch relation into Z boson and Higgs boson. Then one of my colleagues asked me an interesting question. So I was assuming all the scalar particles are heavy decoupled, so alpha mixing angle and beta mixing angle in the scalar sector are related. But what if heavy Higgses are not decoupled and 125 GeV Higgs boson is a mixture of lighter and heavier Higgs boson? Then how is Goldstone Equivalence Theorem apply and do Higgsino relations still hold if we have to add all those Higgs boson effects to get those relations or not? He was wondering, and I couldn't answer at first, so I need to think of this in other angles. So here's a 2 Higgs doublet in gauge eigenbasis in general. So they are written in this way. But we can always rotate it to the Runge basis or Higgs basis, where only one doublet contains all the bath, and the other doublet doesn't contain any bath.
So this is Higgs basis.
Sorry?
So this is what we call Higgs basis.
Yeah, sometimes Higgs basis, sometimes Runge basis. I prefer Runge because Runge is my fifth grandfather's academic lineage. Anyway. Yeah, so in this Runge basis or Higgs basis, so one doublet contains all the bath, and its CP, all the components, is a Goldstone by definition. But CP even Higgs boson doesn't have to be a mass eigenstate. It's just general combination of mass eigenstates. But if I further assume alignment limit, this CP even components becomes a mass eigenstate, and this one becomes exactly the 125 GeV Higgs boson that we observe. So with Runge basis and alignment limit, and also applying Goldstone Equivalence Theorem, Higgs boson and Z bosons are fully included in a one doublet. So this is the basis of my argument. And we don't need actually the decoupling of the heavier scalars. What we need actually is the alignment limit. Usually alignment limit is achieved by decoupling of the heavy scalars, but it doesn't have to be. It's a partial solution. Even if heavier scalars are relatively light, you can achieve the alignment limit. And then this relation is still true.
So this gauge boson and the Goldstone boson G0 becomes a pure Z only at its alignment limit.
Sorry?
This is G.
G.
It becomes the Z boson is only at the alignment limit.
It doesn't have to be. In the Runge basis, yeah, full G is included here. And using Goldstone Equivalence Theorem, this becomes a longitudinal Z. Yeah, but alignment limit makes this CP even Higgs component becomes a mass eigenstate.
Alignment limit means that
Beta and alpha are related.
Higgs to back boson coupling very stable, right?
Oh, yeah, exactly. But that doesn't mean that heavier scalars are decoupled.
Right.
Yeah. So this was a little bit more general proof of the relation. So back to Higgsino dark matter. So now I consider Wino NLSP and Higgsino LSP and discovery prospects and exclusion prospects at 100 TeV collider. So 1 TeV Higgsino could give you the right thermal relic density, but it's not discoverable at any Wino masses. But it could be excludable with not much heavier Winos. So it's a kind of hopeful, kind of also pessimistic. We want to discover 1 TeV Higgsinos and test it. But discovery is not possible, but exclusion is still possible, maybe. But this search is not optimal for Wino dark matter because Higgsinos production is much smaller. The Wino dark matter is much heavier. So we have to rely on something else for Wino. Now I'm going to talk about new limits on light stops from stoponium. So here's the current stop limits. I'm assuming there's no lighter trigenos, so stop can always decay to top LSP, or 3-body WB LSP, or 4-body B Fermi and LSP, or there can be a flavor changing decay into C and LSP. In this region, 2-body decay into top and LSP is just prompt and dominant. And in this region, 3-body decays are dominant. And in this small mass splitting region, either 4-body or flavor changing 2-body decay is dominant, depending on your flavor physics. But there are lots of loopholes. Here, when mass splitting is very, very small, smaller than B or C quark masses, or here, where the mass splitting is almost exactly equal to W boson mass, or here, where the mass splitting is equal to top mass, final state particles are produced almost at rest, so they are soft. So it's very difficult to distinguish signal from the background. So the search limit is weak in these regions. So this is inevitable aspects of the feature of the usual collider searches. And also in this region, which is also known as the stealthy stop, where stop pairs are produced, but stop masses are almost similar to the top mass. So when it decays to TT bar and the missing energy is small, and your stop pair essentially look like the top pair plus nothing. So it's very, very, in this region, stops are very, very difficult to distinguish from top pair. So it's known as a stealthy stop region. And there are a couple of theoretical proposals, such as measuring the top pair spin correlations, which will be different for the true top pair production and the decays of the stop. And also, there are proposals to measure various distributions in the top pair productions. And they have been indeed measured very recently, and they have some sensitivity in this region. But it's very difficult. And this is the status. And of course, if you can wait for more data, then some of the region can be covered. But overall, this similar shape will be shifted to the higher mass scale. And you still have this feature in the higher mass scale. The stoponium can potentially cover all these regions without such features. And bounds will be a vertical line. It doesn't depend on the mass splitting between stop and LSP. So let me introduce what stoponium is. Stoponium is a bound state of the stop and the anti-stop bonded by QCD Coulomb interaction. And it's a spin zero particle, CP even, and color singlet. So quantum numbers are same as the Higgs boson. And once they are formed, stop and anti-stop can pair annihilate into glue and diphoton WWZZ, Higgs through this kind of diagrams. So final states are similar to Higgs boson, but different branching ratio. So stoponium can be discovered through any heavy Higgs resonance searches in the diphoton, WWZZ, and Higgs. It will just look like a resonance in those invariant massive distributions. When the stop mixing angle is small, they almost always decay to glue at 100%. And small branching ratio to diphoton. But because diphoton channel is so clean, diphoton search is best with the stoponium. And here's the atlas limit on the stoponium searches, diphoton searches in the heavy mass region. And blue is the stoponium prediction in our calculation. Roughly about 150, 130 GeV stops are excluded from the stoponium searches, irrespective of your mass splitting. So all those loopholes in the standard searches can be covered up to those mass ranges. But there are interesting conditions to have this interesting phenomenology. First of all, staponium has to form. What are those formation conditions? So anti-stop has to produce with a small relative velocity. So they move with the relatively weakly and give them enough time to form a bound state. So they form near the stop pair threshold. So cross-section is small. That's the bad thing. And stop decay has to be slow enough so that stop and anti-stop have enough time to form a bound state. So binding energy is 1 GeV. So stop decay roughly has to be smaller than 1 GeV. So here I show you the stop decay width as a function of stop mass for the fixed LSP mass. And binding energy 1 GeV is here. So in the most of the stop mass, the stop decay is slow enough. And interesting comparison is toponium. So top and anti-top bound state. Before the top discovery, people have seriously talked about toponium. But after the discovery, we do not see any toponium because top mass is too heavy. And we know that top decay width is about 1.5 GeV. It's too heavy, it's too large to allow a toponium formation. But when we did not have a top discovery, and when we thought about 40 GeV, 20 GeV top quarks, it could have been really formed at that time. But it's not anymore. So this is a condition for the formation. But even though toponiums are formed, they have two options to decay. Either annihilation of stop and anti-stop, or individual stop can still dominate the stoponium decay. So you have to compare stoponium decay, annihilation decay, versus individual stop decay. And individual stop decay has to be small. Otherwise, you don't see a resonance-like feature of the annihilation decay. So here I compare individual stop decay here versus stoponium decay. And this is where the boundary between three-body stop decay and two-body stop decay. So roughly speaking, as long as two-body decay into top and LSP is prohibited by kinematically, you have a dominant stoponium decay, and you can see a resonance-like feature. That's a commonly known statement. But interesting thing is here, even in the two-body phase space near the threshold, stoponium decay can dominate. And that's exactly where the current searches have a weak sensitivity. So stoponium can have a potential to fill this gap in this region. So in this red shady region is where stoponium annihilation decay is larger than stop individual decay. And indeed, in this two-body phase space near the threshold, stoponium annihilation can still dominate. And in this region, roughly coincide with the region where the current searches are weak sensitivity. Oh yeah, so this region was the stealth stop region, and this could also be probed by stoponium. And by requesting current diphoton searches, WWZD boson searches, so current exclusion reach of the stoponium is here, 130 GeV or so. So this stealth stop region is not probed yet, but can be probed in the near future at 14 TeV. According to our preliminary study, 14 TeV 30 inverse femto1 can cover some of this region, about 200 GeV.
Sorry, so when I say the stop needs to be slow enough,
Right.
What's the quantity we should compare? Is it binding energy?
Yes, slow enough.
I mean, you don't slow enough so they will form a bound state, but not just fly away.
Roughly speaking, near the 2M star, they will be formed, and away from the 2M star, usually they don't form.
Like how much?
1 GeV, 2 GeV.
Oh, okay.
So binding energy is 1 GeV, right?
Mm-hmm.
So 1 GeV below the 2M star, stoponium will form.
Mm-hmm.
So invariant mass spectrum will look like, so this is the invariant mass spectrum. And if you didn't have any bound state, it will start at 2M star.
Mm-hmm.
But if you have a bound state, there will be a slight peak here. And this difference is about 1 or 2 GeV, depending on the binding energy. So staponium almost always forms near the threshold. Otherwise, they are too energized.
Do you have an under control framework for really calculating the decay distributions when the stop decay rate is becoming comparable to the annihilation rate? So near that red line, because it's very interesting to know how far you can push in that direction, right? So you would really like to say that you have your calculations at least are under control there, and so I'm asking you, are they under control?
I think individual calculation of annihilation and individual decay is independent, so it can be still applied in this region. But the question is, what's the exact condition for the staponium annihilation to be observable?
Maybe it's trivial. I mean, I'm just wondering if you have these two completely different decay modes. Do I just really I sort of think it just decays by one or the other, and and I just compute the probabilities independently and just add them, and there's nothing else.
That's what it
That's what it is.
Yeah.
Okay, and we just have to think about it.
Just in terms of annihilation, this slide is nothing special.
Yeah, I guess you could just think of them as different Feynman diagrams for the same
different
state.
Feynman diagrams, different processes. No
There's
interference.
that's right. No, they really are different final states. So yeah, it's fine. Good. Right. Okay.
Yeah, but that's an interesting question.
No, it's fine. Okay. You don't have any plots of that, right?
Yeah, I don't know.
Okay.
Okay, so this is all I taught, and summary for the prospects. So gluino pair production at 100 TeV does not definitely cover Wino or Higgsino dark matter, but 200 TeV may be able to probe Wino dark matter in the AMSB scenario. And 1 TeV Higgsino dark matter can perhaps be excludable by a multi-lepton NLSP Wino productions at 100 TeV, but not still discoverable. And staponium can give you important complementary limits on the light stop. It's very easy searches, so this should be seriously carried out and interpreted in terms of staponium. And also summary of future SUSY. So for the gluino pair searches, the results can be presented for the gaugino mass ratio, because gaugino mass ratio can be a useful parameter. And the resummation of scale hierarchy still leave 20 to 30% uncertainty, so better calculation may be needed. And for the electroweakino pair prediction, Goldstone Equivalence Theorem was generically and inherently applied, and Higgsinos phenomenology was especially simplified with this relation without any parameter dependencies. So, yeah, this is all I prepared. Thank you for your attention.
So if the stuff are very heavy, and then they are produced, and then they might also move slow.
Yeah, they can still.
They can also form this.
Yeah.
Can there be a bound for? Can there be a bound for using this for heavy stops?
I think the feature is exactly the same. Just the mass scale is heavier.
But usually they decay very rapidly then, because when they have two-body decay,
All right, that will
so just the
dominate.
individual stops will decay so quickly that they'll never form the down state.
Right.
Okay.
Yeah, it grows with the stop mass quickly. This will go up and cross this line at some point.
Oh. I see.
So, is there any improvement that one would need to make to the diphoton search to search for this?
Any improvement? I think
I
it's a
mean-
fairly simple search.
So, just the Higgs searches or heavy resonance search applies directly, or there's something more that you would want to do?
I don't think much, but one thing we recently noticed is, so this sigma is actually the sigma fiducial. So they wanted to restrict it to a certain rapidity region where the sensitivity is mostly model independent, but they don't use a full coverage of rapidity. That might be one thing we can improve. That's mostly order 1 factor, but still one thing we can improve. And the mass resolution may be another factor we can improve. Staponium is a very narrow width, so if you have a smaller invariant mass resolution, you can diffuse more background and you can have a sharper signal. Otherwise, it's a fairly simple search, I think.
Well, I mean, the Higgs peak is already completely dominated by measurements, right?
Right.
So it does help you to have a narrow resonance.
Right. So if you have a lower resolution and a better resolution, you can reduce the measurement error. Yeah, already here.
I'm sure
Blueband
they already
criteria.
tried very hard to make the resolution as good as they could, no? I mean, I don't know.
So these blue bands are theory uncertainty, and these are mostly experimental uncertainty. Yeah, experimental uncertainty still.
But what is this thing about not using the full rapidity range? I mean, is there something about, is there a different, is it just not as worth it for the Higgs to go to the forward region
For
or
Higgs,
something?
it's not. I mean, if we have a certain model, you have to do as best as possible. But here, they do a general Euclidic searches, and they want to be as much as model independent. Yeah, that's what I know.
So you're saying you could even put in the rapidity distribution and somehow weight your likelihoods
Right.
with that.
I mean, if we just want to test the Staponium, just use the Staponium model, and there's no model dependency. Right? Just Staponium. That's it. You can test the Staponium using full range of rapidity.
Another question for Sunghoon? If no, then thanks for